Dr. Sandeep, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. In this session, we are going to discuss about the imperfections in solids. So, till now we have studied different types of solid structures, different types of atomic structures, and how to resolve them to find out the atomic number, atomic packing factor, all those things. Now, in this session, we are going to find out what are the types of defects are there in these solids. So, what are these imperfections? So, any material will not have 100% a good quality. So, somehow, somewhere you will find some defects. So, how to classify those defects are being discussed in this session. So, mainly these defects will influence the properties of the material. So, what is happening here? The properties of some of the materials depends upon the impurities. If the impurity level is very, very high, so what happens? The properties will vary. So, in order to have a good properties, these imperfections have to be identified, and if any possibility is there, these imperfections can be resolved. So, that's why mainly these defects will influence the properties of mechanical as well as physical properties of any type of material. In general, we cannot find 100% pure material. Every material will have some defects. So, how to identify those defects? We'll see now one by one. And what is the influence? So, main influence is what? The physical properties. So, these structure imperfections will influence the properties of the material. That's why you have to have some knowledge on these imperfections. So, that's why before selecting any material to the required application, one need to know the properties. Before going to those properties, again you have to have the knowledge of what are the types of defects which are available and which is having the metal which is having inside. And how can you see these defects? You can't see physically. You have to see through microscope structure. Through microscope only you can see these structure, as well as you can identify the internally defects, whether it is a line defect, point defect, or any vacancy type of defect. These defects can be identified through microscope only. It cannot be identified through a naked eye. That's why one need to have the knowledge and the importance of these defects in order to identify what are the types of defects and how these are affecting the properties of the material. So, now in this process, the structure, the properties, and the performance. So, how many things we are having here? Processing, structure, and properties, as well as the performance. So, these are all the dependent on the defects on the solids. If you want to have a good performance, the material has to have a good quality. If it is having defects, then the performance will come down. In the similar way, the properties will also come down when it is having more defects. The structure will vary depending upon the defects. So, all these values will vary depending upon your defects in the solids. That's why before going to any application process, you need to control these defects in order to have a good efficiency in the structure, properties, as well as the performance. That's why these are all the parameters which are influencing the defects in the solids. That's why one need to know the knowledge as well as to study the imperfections in solids. So, what are those imperfections in solids? We'll see one by one. Now, for the processing of the silicon as a semiconducting material, it is important to specify the impurity concentration in appropriate units. So, in order to do the processing of silicon in a semiconducting material, so what we need to identify? We need to identify the exact impurity concentration. If you don't know the exact impurity concentration, then the silicon cannot be used as a semiconducting material. So, that's why these impurities or imperfections has to be quantified. You need to quantify, and you have to tell in appropriate units how much amount of these impurities are there in a silicon and how it can be used as a semiconducting material. So, that is one of the point, the imperfections in solids, and the development of the desirable mechanical properties. So, if you want to have enhancement in the mechanical properties, then one need to identify what are the defects in those materials. So that's why development of the desirable mechanical properties. You need to improve, you need to develop, you need to enhance the mechanical properties. How means you need to know the specific of the impurities. What type of impurities are there in that material? If you can identify, then it is very easy for us to enhance, or you can get the desirable mechanical properties. So that is one of the criteria of the defects in the solids. Then the mechanism of hardening or strengthening or to increase the stiffness of some alloys in the steel. So this will affect the defect as a dislocation. So what is happening here in a crystalline structure? If it is having the defects, what is happening? The hardening, the stiffness, as well as the strengthening of the material will go down. And how can you identify these? Means depending upon the crystalline structure, there is some dislocation, whether in a line dislocation or some point dislocation. If any structure is there, in this structure, one point is being removed. What is happening there? The structure orientation will change. There is some dislocation. Because of these defects, the structure is completely changing. It is getting into dislocation. So that's why one need to know the type of impurity or type of defect in order to control all these properties, and you need to quantify how much amount of impurities are present in that material for the given application. And since everybody know that there is no 100% pure material, that's why thus far it has been tactically assumed that perfect materials are existing. We are just assuming that 100% pure materials are existing, but to the fact there is no 100% material which is having a good quality pure material. Even in the pure material also there are some impurities, but we are assuming till now. But now in this case, how to identify those imperfections? We'll see now. Now, all the materials which are containing some defects are called the imperfections. What does an imperfection means? An idealized solid body which is having some defects is called as imperfections. Now, as a matter of fact, many of the properties of the materials are profoundly sensitive to the deviation of the crystalline structure. So, if any deviation is there in the crystalline structure, that means it is influencing the properties of the material. That's why these crystalline structures without defect, if anything is there, then it is called as a perfect material. If the crystalline structure is changing or it is being dislocating, so that means that there are the defects. That means this is influencing the properties of the material. So that's why the properties of the material are profoundly sensitive to the deviation. If small variation is there in the crystalline structure, the properties of the material will also change. So that's why sensitive to the deviation of crystalline imperfection. So what is happening? Because of that, it is influencing not only the properties, also adverse effect on the specific characteristics. So not only the properties, it is giving some adverse effect on the characteristics of that material. And how you need to control these things? Once you know the quantity of the impurity, then you can control. You have to calculate how much amount of gaps are there, deviations are there, imperfections are there. Then it is very easy to us to control those imperfections. So, crystalline defect reflect to lattice irregularity having one or more than its dimensions on the order of atomic diameter. So, the crystalline defect, how you can identify means because of the irregularity in the lattice structure. Suppose you have the lattice structure like this uniform lattice structure. Like this, you have uniform lattice structure. Now, how to identify there is some defection? How to identify if there is some defect? That means this atom may come like this. It is changing its position from here to here. Then what is happening? There is some change. So this is the change. That means the crystal structure is varying its shape. It is changing its shape. That means that there is some deviation because of the defect, because of the some point defect. Since the point is moving from this place to this place, there is some point defect. That's why the crystal structure is changing its position. So because of that, what it is being influencing the properties. Before, the properties are very uniform. Now after this defect, what is happening? The properties are varying at this junction, at this point. So it is very influencing the properties, as well as it is giving the adverse effect on the characteristics of the material also. Like that, several different imperfections are discussed, including the point defect. So what is the point defect here? So some atom is being missing, or some atom is changing its position to from one place to another. So this refers to the point defect. Okay, so it can be linear in one dimensional, and which is two dimensional also. It is changing its orientation from one point to another point. So this comes under the point defect. So if you see the point defect, again the point defect, you have vacancy and self-interstitial defect. So what is vacancy and what is the self-interstitial defect? So vacancy, in the name itself you can identify there is some vacant position in the crystal structure. That means there is some gap. So if there is some vacant position in the crystal structure, that means the property or the characteristics at that point is very weak. So before there is no vacancy, it is very strong. But once there is a vacancy or gap in the crystal structure, that means that the properties are being varying. Now you can see the simplest example here. The symbol of the point defect is a vacancy. So point defect comes under vacancy. Okay. So this is the point defect. Point defect comes under vacancy. That means there is some vacancy, there is some gap in the crystal structure. So vacancy or vacant lattice site normally occupied from which an atom is missing. So you can see here the dotted thing. There is some atom which is being missing. That's why it is called as a vacance defect. So in the complete crystal structure, if atom is there, it would be like this. But now what is happening here? There is vacancy. There is no atom in between. So that's why this is called as a vacancy defect, and this comes under point defect. And coming to self-interstitial. Self-interstitial means, so what are the vacant atom is there? So this is slowly moving to this position. So in the crystal structure itself, it is self moving from this position to this position. So this type of defect is called self-interstitial. It is going by in own self. Okay, from this position it is moving to this. So you can observe here clearly there is some atom. Now 1, 2, 3, 4 and this 5 is here. In between all the 4 atoms you have the 5th atom. So this is some bonding. But here you have vacancy. In general, you can identify here every 4 atoms are being bound together. 4. But somewhere you can find here the 5th atom. So in this type of thing. So this is the self-interstitial. That means the vacant atom is moving its position somewhere to here. So this type of defect is called self-interstitial. So these effects will again adversely affect the characteristics as well as the mechanical properties of the material. Now, all the crystalline solids contain vacancies. Every type of crystal contains vacancies, and it is not possible to create such material that is free from these defects. As I said, as we discussed, there is no material which is 100% pure. Every material has its own crystal structure, and in this crystal structure, the atoms move freely from one position to another. So because of these movement of the atoms, what is happening? Some defects are being occurring inside the atomic structure. So in generally, it is not possible to create any material that is free from these defects. And the necessity of the existence of these vacancies is explained by the principle of thermodynamics, and vacancy increases with the entropy of the crystal. Now, how to identify the point defect? So the equilibrium of number of vacancies is denoted by NV. So the equilibrium number of vacancies for a given quantity of material. So this is very, very important. Quantity. You need to find out what is the quantity of presence of impurities. If you know the quantity, not the quality, you have to have the value of quantity value. How much amount of impurities are there in a body, then it is very easy for us to identify the defects, and it is very easy for us to resolve those defects. Now that's why the number of vacancies for a given quantity of material depends on the increase with the temperature. So with the increase in the temperature, the number of vacancies in the material will increase. So this is directly proportional to your temperature. That's why NV, that is the number of vacancies, is equal to N into exponential of minus QV by KT. So what is the NV here? N, Q, K and T. So if you see this expression, N is the total number of atoms in the site. So this N refers to the total number of atoms inside. So how many atoms are there inside can be given by this N. And what is Q here? Q is the energy required for the formation of vacancy. So if an atom has to move from one place to another, there is some requirement of energy. Yeah, is it not? So without energy, the atom will not pass from its position. So there is some requirement of energy. So that energy requirement is given by QV for the formation of vacancy. For the formation of vacancy, this QV is the energy required. And of course, K is nothing but the absolute temperature in kelvins, and T is the absolute temperature, and K is the Boltzmann constant value. So that is 1.38 into 10 power minus 23 joules per atom, or 8.62 into 10 power minus electron volt per atom. So this depends upon the what amount of units you are taking. Okay, now if you want to find out what is the amount of number of vacancies in an atom, then you need to use this expression N V is equal to capital N into exponential of minus Q V K into T. Okay, in this what I told, capital N refers to the total number of atoms. How many atoms are there inside the crystal structure? So these are the number of atoms present in the crystal structure. So this is refers to capital N. And what is QV here? Q is the, so in order to vacate an atom from this position to another position, there is a requirements of energy. So that energy is given by QV. And why we are taking negative means, since there is some vacancy, there is a movement of atom. Okay, that's why you are taking negative. And K refers to the Boltzmann constant, gas Boltzmann constant, that is nothing but 1.38 in 10 power minus 23 joules per atom. And capital T refers to the absolute temperature. So these are the values you need to take in order to find out what is the number of vacancy atoms for a given quantity of matter. Now coming to the, after discussing about point, so in that vacancy defect is there. Vacancy is nothing but one atom is moving from its position and it is creating some vacancy. Now what is this self-interstitial? A self-interstitial is an atom from the structure that is crowded into the interstitial site. That means this vacant atom, what is it is doing? It is moving to another. That's why it is being crowded into the interstitial site. So as I told, so this is the atoms 1, 2, 3, 4. Now slowly whatever the vacant atom is there, that is being inserted here. In between, it is being crowded into the interstitial site. That's why it is called as a self-interstitial defect. Okay, a self-interstitial defect is nothing but it is an atom that crystal is being crowded into the interstitial site. In the atomic structure itself, it is being crowded into that interstitial site. So that type of defect is called self-interstitial. And what it is doing, a small void space that under the ordinary circumstances is not occupied. So because of that self-interstitial defect, what is happening? There is some vacancy. There is some point defect in the complete structure. So in metals, a self-interstitial introduces relatively large distortion. So because of this self-interstitial, what is happening in the metals? Because of the position changing and it is being inserted into the interstitial site, what is happening? There is some distortion in the surroundings. So once, see, in the earlier what is happening? It is exactly packed like this. Now once this in self-interstitial defect is coming, what is happening? It is moving somewhere here and it is creating some vacancy. So what is happening? Because of this vacancy, there is some large distortion in the structure of the material. So because of this distortion, what is happening? There is some change in the position of the atomic structure. So because of this, there are some changes in the properties, and because of that, there is some changes in the characteristics. So one change in the atomic structure, the complete characteristics, the complete properties are being varied. So that's why one need to identify the quantitative amount of impurities in order to describe the defects in the material. So consequently, the formation of these defects is not highly probable, and it exists in very small concentrations which are significantly lower than for vacancies. Of course, though the defects are being identified, these are very small when you compare with the whole atomic structure. So these can be neglected at some point. So you can now observe what is type of self-interstitial defect. So here, before you have a vacancy, the atom is being moved. So where it is being moving? It is moving from this place to here. Now from at this place you have vacancy. So because of this vacancy, there is a large distortion. Distortion is coming. So what is happening? Before exactly it is a cubic structure. Now it's some changing its orientation like this. So it is getting distorted. It is changing its position. So because if this, what is happening? If any body is uniform, then you have a good properties. If it is not uniform, what is happening? The properties are not that much good when you compare with the previous. So in this case also, because of this self-interstitial, the atom is moving into the crowded. So this is the crowded interstitial site, because this atom is inserting, it is trying to insert into this interstitial site. That's why it is being crowded into that. So because of this crowded interstitial site, here you have the vacancy. So because of this, you have a large distortion in the material. And as we discussed, the number of vacancies, how to compute this number of vacancies, you can see this example. Calculate the equilibrium number of vacancies per cubic meter for a copper at 100,000 degrees centigrade. So what you need to do? You need to calculate the equilibrium number of vacancies per cubic meter for a copper at 1000 degrees centigrade. At 1000 degrees centigrade, you need to identify what is the number of vacancies per cubic unit meter. And the energy of the vacancy formation is 0.9, and the atomic weight and the density are given as 63.5 grams per mole and 8.43 grams per centimeter cube. So this is the atomic weight of the copper, and the density of the copper is given by 8.4 grams per centimeter cube. So this is the data given for us. With this available data, you need to identify what is the number of vacancies per cubic meter for the copper at 1000 degree centigrade. Now we have seen this equation. So what is the equation we have to use? This equation, Nu is equal to N into exponential of minus Q V by KT. So what is NV here? Number of vacancies. What is it? N here, capital N? Total number of atoms present in the material. So now in this case, copper is given as an example. So N is here, capital N is the total number of atoms present in the copper, and QV is the energy required. QV is the energy required to create that vacancy, and K is the gas constant, that is constant value, and T is the absolute temperature. Now with this data, you can't directly find out what is the number of vacant atoms. Before that, you need to identify what is capital N. Since in this question, they have not given the number of atoms, before going to that, you need to find out what is the total number of atoms present in the copper. So for that, what we need to have? We have the equation N is equal to NAP by NaCu. That means density of the copper to the atomic weight of the copper. That gives the number of atoms present in the copper. So once you substitute what is the density as well as the atomic weight of the copper, you can get the N value. So N is equal to Na rho by NaCu. We know that the density is given as 8.4 grams per centimeter cube and the atomic weight of the copper is 63.5. Now once you substitute all these values with the Avogadro's number, you are getting total number of atoms present in the copper at 1000 degrees centigrade is 8 into 10 power 28 atoms per cubic meter. So per cubic meter. So in the question also we have per cubic meter you need to identify what is the amount of vacant atoms. So that's why this N, the capital N, refers to 0.8 into 10 power 28 atoms per cubic meter. So after getting this N value, then we can directly substitute in this equation. Nv is equal to N into exponential of minus QV by KT. So at 1000 degrees centigrade, you need to find out 1000 degrees centigrade. So now every value is in Kelvin. So that's why you need to convert into Kelvins. So plus 2 centigrade you can add. So that's why 1273 Kelvins. Now substitute the value of N here. What is the value of N here? 8.0 in 10 power 28 atoms per centimeter cube. And exponential of minus, what is the energy required? Energy is given as 0.9. And what is K here? It is 8.62 in 10 power minus 5. And what is T? 1273. So substituting all these values, you are getting number of vacancies in V as 2.2 into 10 power 25 per centimeter cube. So these many vacancies you are having in the copper at 1000 degrees centigrade with total number of atoms. So total number of atoms you have it as 8 into 10 power 5 28 atoms per centimeter cube. In that you have almost 50% of vacant electrons, vacant atoms. 2.2 into 10 power 25 vacancies per centimeter cube. So these are the things how you need to calculate the total number of vacancies. So this is the procedure you need to follow. So before that, one need to have the total number of atoms. If you know the total number of atoms only, then only you can find out what is the total number of vacant electrons or atoms in the given material. Now, what are the impurities? So before this, we have discussed about the defects. Now, what are the impurities in solids? So, as we discussed, a pure metal consisting of only one type of atom is not possible. So, every material will have some alloys. So, you don't have a pure single material. During the manufacturing of any metal, some alloys are being mixed. So, because of that, some impurities are being added. Okay, so you can't find out 100% pure material. So, that's why it is not possible to create any metal with only one type of atoms here. So, impurities or foreign atoms will be present. So, during the crystalline process, what is happening? Some other material will get into the base material, and because of that, there are some impurities can be found. And what is happening? It is difficult to refine the material to a purity of 99.99%. You can't do this. You can't get 100% or 99.99% purity. There are some defects or there are some impurities during the manufacturing process. So at this level of the order of 10 power 22 to 10 power 23 impurities atoms will be present per cubic meter. So per cubic meter, you can have up to 10 power 22 to 10 power 23 impurities of atoms present per cubic meter. This is very, very important. Per cubic meter, you can have 10 power 22 to 10 power 23 impurities of atoms. So all the atoms are not pure. So most familiar metals are not highly pure, rather they're alloys. So because of these alloys of the metals, what is happening? Impurities have been added, and you're getting some additional different types of atoms. So that's why there are impurities in the solids. So because one need to have a good special or specific characteristics or special properties of the material, we are trying to adding some another material. So because of this adding of another material, what is happening? That is the foreign material. So some alloys are being mixed with the base material. So because of that, you can't get one uniformity atoms of structure. You can have different types. So because of this, you're getting the impurities in those solids. So the addition of impurities atoms to the metals will result in the formation of solid solution. So what is solid solution here? We are trying to additive adding some another material to the base material in the form of a solid solution. Okay, so that's why you're getting the composite materials. How we are trying to get these composite materials means we are trying to add some another material in form of a solid solution to the base material. That's why we are getting different types of materials with composites. In order to have some different types of characteristics, or in order to have good properties, to improve the properties, we are trying to adding this solid solution in the form of additives to get these impurities. And several terms relating to impurities are solute and solvent. So these are all some other terms which are being used in terms of solid solutions. And what is a solid solution means? A solid solution forms when the solute atoms are added to the host material. So host material is nothing but the base material. You have some base material that is called the host material. So for this host material, you're trying to add some additives, that is in the form of a solid, liquid solid form. Okay, solid solution form. So when you add this solid solution form to the host material, these type of solid impurities are being arising. So this, what is happening? It is forming new structures are being formed. Earlier you have a single structure. Now since you are adding some impurities based upon the solid solution, you are getting the new structures are being formed. So because in order to have good properties, we are trying to do this, and in the same way we are getting these impurities also. So now if you see this figure, you can observe what is solid solution. Impurity point defects are found in solid solution. So in the point defect, we are getting that vacancy. Now in the same way, in the solid solutions also, you are getting these point defects. Here you can see the interstitial impurity. So there is some change in color. Why you are getting the change in color and here? Because you are adding some solid solution to the host material. Because we are trying to adding some alloys to the base material or the host material, these impurities, these foreign materials are being coming, and you are getting this interstitial impurity atom. Though we are getting enhancement in the properties, still we are having this type of interstitial defects, and this you need to identify. And here substitutional impurity, some another matter, some another material we are adding. That's why you are getting substitutional impurity. So these are called the defects. Comes under solid solutions which are substitutional, that is adding another material. Because of adding another materials or alloys, we are getting this interstitial impurity in the atoms. And what are the different types of features that are being determined during this process means? First is the atomic size factor. And what is the use of this atomic size? What is the purpose means? These are the features which are being affected because of those solid solution impurities. So the quantities of solute can be accommodated in this type of solid solutions only when the difference in the atomic radius between the two atoms, and this atom should not be less than plus or minus 15%. If it is not less than this value, then atomic size factors can be influenced. This can be changed and this can be distorted, and you'll have the different new phase is being formed because of the solid solutions. Next, the crystal structure. The structure of the crystal will also vary because of that solid solution impurities, because of that self-interstitial atom and the point defect. These crystal structures are being changed into different types. Electronegativity. So because of the more electropositive one element and more electronegative another element, what is being happening? Because of this interatomic compound solutions are there, these are being affected. And valence electrons are being found in these things. And another type of defect is what? Dislocation. This comes under linear defect. So if you have uniformity in the atomic structure, but once one line is being varied, what is happening? There is some dislocation. So you can see this figure clearly. you can observe there is no uniformity. Here you can observe the uniformity in the structure, but once you come down, there is some distortion. That means if one atom is being removed, and you're creating some vacancy in the atomic structure, so there is some deviation, there is some dislocation, there is some change in the line. That's why you can get irregularity. So this you need to identify. So a dislocation is a linear or one-dimensional defect around some of the atoms are misaligned. So because of that vacancy, once the atom is being vacated, so the alignment is being changing. So that's why you can observe in this figure there is some disorder in the linearly. In the linearly, you're getting this dislocation. So this is one of the type of linear defect. So the atom position around an edge location, extra half of the plane atom is shown in this textbook. So that's why if you remove up to this, you can get a good linear thing. Now once the atom is being removed from this, so you are getting some dislocations like this. Linearly it is being changed. So this is one of the type of dislocations with respect to linear. Screw dislocation. Because of the shear force between the two materials, when the two materials are being sheared between each other, what is happening? There is some screw type of defect is being coming. So you can observe clearly this position is being screwed. So this is mainly because of this shear. One atom being colliding with another atom. So there is some shear force. So because of the shear force, this screw dislocation is being formed. So this screw ligation may be thought of as being formed by shear stress that is applied to produce this distortion. So main criteria is what? Shear stress. So because of this shear stress, you are getting this screw dislocation. So you can observe clearly dislocation line from here up to this point. You are having uniformity in the structure, but once the shear force is applied on the body, what is happening? There is some change in the position. You are getting some screw dislocation here. So this is one of the type of dislocations. So this is how, what are the different types of defects you can observe in the solid bodies. And if you want to have the references, you can go to this Introduction to Physical Metallurgy, and the other book is Essential of Material Science and Engineering, and third one is Material Science and Metallurgy. The last one is Material Science and Engineering. So these are some of the references where you can get the information about the different types of defects and what is the influence of these defects in the solid bodies. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.